Yes.
Well, voilà.
I can quickly introduce you, maybe, Professor. So welcome, everyone. We're very happy that today's speaker of the colloquium is Professor Pierre Dersin. So let me say a few words about him. So he's currently an adjunct professor in operations and maintenance at Luleå University of Technology. He holds a PhD from MRT, and furthermore also works as a reliability, availability, and maintainability director, and also a PHM architect at Alstom Digital Mobility. So today's talk, as shown here on the screen, is titled Characterizing RUL Loss Rates. And we're very happy. Oh, I'm forgetting one thing, that Professor Dersin is, of course, also in the advisory board of the PrimaVera project, not to forget. So we're curious to your talk.
Thank you very much for the invitation. Good afternoon to everyone. I'm sorry for this little technical problem in the beginning. We'll try to make up for it. And so now I have to push the, yes, I have to use this. Okay. So just a very few words about Alstom and Luleå. Alstom is a big railway equipment manufacturer, rolling stock, signaling and infrastructure, but now it's becoming a provider of mobility solutions, and that includes maintenance. So since the acquisition of Bombardier Transportation, we now have about 75,000 people worldwide in 100 countries, so it's quite a lot. And then I'm also, as mentioned, with Luleå Technology University in Sweden in the operations and maintenance engineering. They have in fact what's called a Luleå Railway Research Center, which dealing primarily with reliability, maintenance, and has very practical things like test beds, etc. And works with a lot of private companies. So today, after an introduction to the concept of RUL loss rate and MRL, I'll discuss a special class of distributions, those which have an MRL, mean residual life, linear with time. Then we'll generalize in two ways. Then we'll end up by taking a look at multiple failure and degradation modes and conclude. The results I'm going to present are preliminary. They're still ongoing work. There are not so many examples as I would have liked because of data which is confidential, but I think that the idea is to give you the goal is to give you an idea of an approach which is based on the classical reliability, but at the same time touches on the needs, I believe, of PHM and predictive maintenance. And of course, I would be eager to have your comments and feedback. That's the goal, I believe, of these seminars. So, introduction. Predictive maintenance, you all know the idea of predictive maintenance. It is to monitor degradations in assets and intervene. It is maintained before the failure takes place, while it is still time. And hence the concept of remaining useful life from time t. How much time do we still have until a complete failure takes place? That is, until the function is lost. And the idea of predictive maintenance is to perform maintenance not too early, so as not to do excessive, costly systematic maintenance, but also not too late, so as to avoid the failure. So the concept of RUL, how much time we still have, is obviously fundamental. And there is uncertainty. RUL is not just a number, it has to be presented with a confidence interval because there are several sources of uncertainties. Uncertainty in the model parameters, uncertainty in the measurements, and uncertainty in the future load of the asset. So we have this curve, which is a sort of, let's take an example of a fault, which could be a crack, for instance. You can think concretely about it as a crack. So its size is growing. And here we have to extrapolate to know when it will hit a threshold where really it's too much and the fault and the function is lost. So if we work in a deterministic way, the point will be here. But because we want to take uncertainty into account, really can only give a confidence interval, which can be more or less narrow depending on how much knowledge we have of the project, of the system, and how many data we have. So this is a key in what I'm going to discuss today. And then there is a concept of RUL loss rate. So start with a certain value of the RUL, and as the asset degrades, it decreases. And okay, it may reach the acceptable limit sooner or later. And so the idea is how fast it decreases. So, you know, the Dutch proverb, the tijd gaat snel, gebruiken we wel. So this is a sort of illustration of how precious time is. We have to make the most with what's left. And this, by the way, slide is borrowed from Professor Kumar, who is the head of the Operations and Maintenance Division in Luleå. And today I'm going to discuss this question of RUL loss rate. Now, PHM, Prognostics and Health Management, relies on data science and physics of failures. There are data-based approaches and physics-based approaches and combinations. But what I would like to argue today is that reliability theory, classical reliability theory, can be useful as well. RUL is the remaining time to failure at some instant t, given that there has been no failure before time t. And so we can speak about the conditional expectation of that value, which is called the MRL, the mean residual life. So it is the expectation at time little t of the time that remains to the instant capital T of the failure, given that there has been no failure before little t. Okay, so this is the expectation basically of the RUL. Properties of MRL have been studied for ages. It started in the 1960s with Barlow and Prochen, but they can help with PHM. Now, a failure doesn't have to be something that breaks down. It can be just the loss of a function. It could be the pseudo failure. For instance, we have a health indicator, and the failure takes place when the health indicator crosses a certain threshold. So it's a fairly general concept. So what do we know about MRL? First of all, the notion of loss rate. So it's basically the derivative of the RUL with respect to time. So if you can interchange expectation and derivative, then we are interested in the expected loss rate, which is the derivative of the MRL with respect to time. So this, we started, and this may be a sort of theoretical study, and yet I'm from industry, but we actually have been confronted with that at Alstom, because there are quite a few things that were in a way which is linear with time. It, of course, does not apply to every type of asset, but for instance, things like the pantograph, carbon strip wear, the wheel wear, it is reasonably argued that it's a question of material loss, basically, and the wear can be really reasonably argued in many cases to occur in a way which is linear with time. So what properties characterize time to failure distributions which have an MRL which varies linearly with time? This is a question we asked. And actually, I looked at the literature, and there is not much on that, actually, on that particular question. So what the remainder of this talk today, first we'll study this simplest case when the MRL is a linear function of time, and we will characterize the distributions that have that property. And then we'll generalize first by considering functions which are piecewise linear, and then in a second way by transforming time so that in the transformed time we have a distribution which is linear in time. Then we'll end by discussing briefly concurrent failure modes. Notation-wise, from now on, instead of MRL of t, I will simply write V of t, which is more convenient. So first, we look at this special class of distributions that have an MRL, mean residual life, linear in time. By the way, do not hesitate to interrupt me through the chat or otherwise. You may wait till the end, but if there is something that is not clear, don't hesitate to interrupt me. So first we have to remind a few key relations which link together the various quantities that we are interested in. First of all, the reliability function, of course, that R of t is the probability that the time to failure, capital T, exceeds little t, okay? So it's R0 is 1, etc. As t goes to infinity, it goes to 0, it's decreasing. The failure rate or hazard rate, it's the opposite of the quotient of the derivative of RC to R of t. Then we have the mean residual life, which is an integral, okay, so it's conditional expectation. And V of 0 is the MTTF, mean time to failure. And it's very easy to, by manipulating those variables, to see that we have this relationship. The time derivative of the MRL is equal to lambda, failure rate, function of time, times the MRL itself minus 1. And then we have the inverse formula, which is an integral formula, which gives the reliability function from the MRL. So, in fact, once you know one of these three functions, you know the other two. If you know the reliability function, you have the failure rate and the MRL. If you know the failure rate, you have the reliability function and the MRL. If you know the MRL, you have the reliability function and the failure rate. So these are things. This is, of course, classical. But sometimes this relation is not always well known, or it's kind of forgotten, and we'll be using it. So this is why I was reminding it. So if we now look, by the way, yeah, it's interesting to look at this differential equation and to see how it can be interpreted. So we write it in a differential form here. And what it says is over a small time interval dt, dv of t is the loss, the average loss of RUL, right? So we can see that actually it's usually less than dt, because this is actually less than 1, because dv over dt is negative. The mean residual life goes down as time goes on. So what it means is that when 1 hour goes by, the average RUL loss is in general less than 1 hour. It could be 1 hour, but usually it's less. So this is a physical interpretation, so to speak, of this equation. Now, the family of lifetime distributions with an MRL linear in time. Why is that family important? Why is it worth looking at it? First of all, as I said, because it accurately depicts some physical phenomena, not all of them. Second, because if you take any continuous functions, you can approximate it by one which is piecewise linear if you have enough pieces, although it's not always that convenient. And third, because it contains important special cases, and we'll see this in a moment, the exponential distribution, the uniform distribution, and others. And yet, in the literature, personally, maybe you have seen it, but I have not been able to find any study of this class of lifetime distributions. So we did it. It's not too complicated. It's enough to use the equations that I reminded you of before. So what does it mean? If the MRL is a linear function of time, so two parameters, mu, which is the MTTF, V of 0, and k, which is a slope. So generally, it has a finite support from mu to mu over k. But of course, if you let k go to 0, the finite support becomes infinite. So k is indeed the expected loss rate. So we take this equation, which I reminded you of, and immediately from this equation and from this definition of V, there follows the expression for the failure rate, which is this. And there follows the expression for the reliability function, I wrote it D, not to be confused with R, which is generic notation. So we find this formula, which includes the loss rate, K, and the mean, mu. And it says finite support, okay. So now, if you look at special cases, so general K is between 0 and 1. If you make K equals to 0, then the MRL is constant, it's the MTTF, and we have the exponential function, where there is no RUL loss. The mean residual life throughout time is always constant and equal to MTTF. No aging, that's well known for the exponential distribution. If you look at the other extreme and K is equal to 1, that means, so for the exponential, that means that for a time interval dt, the loss of RUL is 0. No wear, no aging. In the opposite extreme, if you put k equal 1, then we have the MRL, which is t minus t. The remaining useful life, or the average remaining useful life, is simply the difference between the time of death, let's say, and the current time. So it's deterministic in that case. So it's a maximal possible loss. For every hour that goes by, one loses 1 hour. Then in between, by the way, if you take k equals 1/2, then the mean remaining residual life at time t is a half of the remaining time. So this is actually the uniform distribution. For every hour that goes by, the average loss of RUL is ½ an hour. So this is the same in pictures, exponential distribution. There we go. V of t is constant. And from the general equation, there follows the usual relationship, lambda is equal to 1 over MTTF. And by the way, the average engineer knows only that. You know, I've been spending about 10 or 15 years now telling people this is only true in a very special case. But since our competitors do the same mistake, that's okay. But it's only a very special case. And the reliability function is an exponential. At the other extreme, I call this a Dirac distribution because the reliability function is a step function. So it's 1 until a certain time, capital T, and then becomes 0. It is certain that the asset will live to that time, but it's certain that it will not live 1 second more. So in that case, this is the mean residual life. And from this equation, you find that the failure rate is equal to 0 until the, I think this should be mu. There's a mistake. It's not 0, it's mu. It should be 0 until mu, and then it jumps to infinity. So it's an impulse function, hence Dirac. And then in between, you have the uniform distribution, where the mean residual life has a slope of 1/2, and the reliability function also is linear, the same slope of 1/2. So it goes from 0 to twice the mean, and the nice formula for the failure rate. So in general, we have this table which summarizes all the special cases in the general case. So in the general case, this is the reliability function, the mean residual life, the failure rate, and the derivative of the MRL is minus k. Exponential k equals 0, exponential function for the reliability function, constant MRL, and constant failure rate, which is reciprocal. Uniform linear function for both the reliability function and the MRL, and the Dirac, where we have a step function for the reliability function and a linear function, but simple, and impulse function for the failure rate. So this is interesting because one can use that to build confidence intervals. The conditional distribution of the survival time after time t is, of course, the ratio of the reliability function at time t plus s by the same at time t. So we can easily calculate this function as long as t is between 0 and mu over k, and then it becomes 0. And from that we can obtain confidence bounds. Let's say the confidence bound at the 1 minus alpha level is given by this lower bound and upper bound. So this is the case. And this is the case for k equal 0.6, fairly small value of k. And to the right, you have the same for k equal 0.9. And an interesting property is that when k increases, the interval becomes narrower. So what does that mean? When the aging or the loss of RUL becomes higher, there is less uncertainty. It's intuitive. If the asset ages very fast, we have a very high dynamics of degradation, then there is little uncertainty. It degrades very quickly. But when the dynamics are slow on the opposite end, of course, there's more uncertainty as to exactly when it will fail. And this property is illustrated by this figure. It shows the width of the confidence interval as a function of the, what I call the aging rate is the slope k. So this is basically what I said. The higher the loss rate, the narrower the confidence interval. And in the limit of k going to 1, that is deterministic aging, the confidence interval goes to 0. So this is indeed deterministic. And at the opposite end, when k goes to 0, we have the exponential distribution, which has the highest confidence interval of the family. The width is given by this well-known formula. And this can actually be materialized if you calculate the variance of the distribution. You have then the coefficient of variation, which is given in terms of the slope k by this formula, which actually can be inverted, and you have this. This is called the homographic law, something. So it shows the relation between the aging rate and the coefficient of variation. So once again, the faster the asset degrades, that means the higher k, the less uncertainty as to when it will fail, and therefore the lower coefficient of variation. The two extreme cases, exponential no aging, maximum uncertainty, deterministic full aging, and no uncertainty. In between, you have the uniform function, and this formula provides the well-known result. Coefficient of variation is 1 over square root of 3. So if we have a way to estimate the aging rate k, for instance, by maximum likelihood estimation or by Bayes, then we have the coefficient of variation. And conversely, if we can estimate the coefficient of variation, we have the parameter k. And actually, what I showed was the coefficient of variation of the time to failure, but we can also apply this calculation to the coefficient of variation of the RUL, which is more interesting. And you find this, and you find therefore that this coefficient of variation is independent of time for this class of distribution. It's always the same formula. And now, if we look at not a linear case, but a generalization through a piecewise linear function of time, let's say there is this knee here. So we have this slope until time t1, and in this particular example, fast slope until time t2. Then we can apply the formulas we saw before, the reliability function until t1, and then to live until this time, you have to live first until t1, hence this factor, and then you have to live for the remaining time from t1 to the time you're interested in. So you get this formula for the reliability function, and that can be used to derive, of course, a probability density function, and then you can use estimators for k1 and k2. But the challenge here is to detect the knees in the function. It is the change of slope in the mean residual life. And of course, these changes in slope are linked to the changes in the coefficient of variation. So this is an area of investigation, because it's easy indeed to generalize, but then we have to find the parameters. So what we have looked at so far is the special class of distribution with MRL linear with time. Then we have hinted how it can be generalized to a piecewise linear function for the time to failure. But before I go further, if there are any questions on the previous part, please feel free. I hope it was reasonably clear, but I can answer questions you may have.
Can I ask one question?
Of course, please.
Yeah. So what you show is the link between remaining useful life, which is typically looking at the remaining lifetime at any moment, and you connect it to the reliability field. But is then the main difference between these two that in reliability you always start from the beginning, so you only look at the complete life and not at the remaining life? So that's the connection that you propose now.
Yes, but here in reliability we can also look at the remaining life by looking at the survival distribution instead of distribution from the beginning. This is what we do here, right? This is the, what was it? Survival distribution is, yeah, this, I will find it here, yeah. This is given that we are at time t, what is the probability of surviving at least time s after time t. So we really look at the future from time t. Huh?
Yeah, okay.
Any other question? Well, we'll continue. You can still ask question at the end. So now, of course, this family we looked at of lifetime distributions which have a linear MRL, an MRL linear in time, is a special case. And even if we can always consider that we can cut it into small intervals and it becomes piecewise linear, still it may be artificial in some cases. And it certainly does not include well-known distributions like Weibull, log normal, gamma, etc. So how can we generalize the results obtained for this special family to other families? And what I've done is to generalize to distributions which are characterized by two parameters. This is, by the way, the case of all these distributions here. And the idea is to use a time transformation. So I don't know, you can review those presentations 100 times. There will always be residual mistakes. So I apologize for this, but so this is simply G of t. But I will correct in. So this is not, I don't know, this G is a transformation which define t prime as a G of t. Okay. So we define the transformation of the time in such a way that in the transformed time, t prime, the time to failure has an MRL, which is a linear function of the time t prime. So it's a little bit the same idea as those of you who know the support vector machine. We do a nonlinear transformation so that in the image space, you have a separating plane, which is, and then you come back to the initial space. Here's the same idea. We transform the time into another time space, let's say, where things are linear. And we have to impose a constraint. To impose a constraint that the reliability function in the transformed time is the same as a function of t prime as a reliability function in the initial time. Then we can use relationships to identify the parameters mu and k, because in the image space, let us say, the MRL will be a linear function of t prime, so it will have some parameters mu and k. And because we have imposed that the two distributions are the same, in particular, the expectation will remain the same and the variance will remain the same. So that will allow us to determine these parameters mu and k in the image distribution. So now we have to find this transformation. And in fact, I'm saying that the transformation which solves the problem is this one, where by definition, mu is the expectation of the time to failure of the initial distribution, and k is defined like this, in the usual way. You can see that as time moves from 0 to infinity, the image t prime, it goes from 0 to mu over k, so it's on finite interval. So the proof of this is actually straightforward, because the image in the image space, the reliability distribution is the same as the initial reliability distribution. From the definition of G, which we have just taken there, we derive R of t. It's expressed like this, but if we put G of t equals t prime, this is the formulation for the reliability function of a time to failure which has an MRL linear in time, with a loss rate gain. So it's like this. So therefore, we have shown that this transformation converts the initial distribution into one which is in the image space as a MRL linear in time. So then we can apply the formula we had in the linear case for the confidence interval and derive a confidence interval in the image time. So this basically is the idea. Use primes. This is the bounds we had before. We replace t by g of t, t prime. And then we invert the transformation. G is a increasing function, and so in general it is invertible. So we can find the confidence interval for the time of failure, and therefore for the RUL, which is the time of failure minus the current time. And so I will give some examples now, which are the distributions which we mentioned. Start with the Weibull distribution. So in the Weibull distribution, this is the reliability function with parameters eta for scale and beta for shape. So here is the G function. So the expectation is given in this way and the variance in this way. So the using what was done before, we can derive the K coefficient as a function of beta only, the shape parameter. The G function is an S-shaped function, which goes from 0 to mu over K. It is usually an S-shaped function. And then we have the K as a function of beta. So when beta is 1, which corresponds to the exponential distribution as well known, gives K equals to 0, which is what we found before, but it's good that we found the same result. And the coefficient of variation is 1. And at the other extreme, when beta goes to infinity, as the coefficient of variation of the Weibull shrinks to 0. And so we have a deterministic function with coefficient of variation 0. So that's, and here we applied what was done before for the confidence interval by just using the formula I've just shown before with beta equal 2 and beta equal 5. And as expected, when beta increases, the width of the coefficient of variation decreases because the coefficient of variation decreases. So this is consistent with what we saw in the linear case, but applied to a very nonlinear distribution with two coefficients. Then another, this is an illustration of the G function. So the yellow case is beta equal 1.5. So we see it's pretty almost like a straight line. But when beta increases, blue is beta 2, orange is beta equal 3, gray is beta equal 4. It more quickly goes to a constant, the asymptotic value mu over k, and so it's of course more nonlinear. When beta equals 1, which is the exponential, the G function becomes a straight line, which is normal because the transformation is the identity. The initial function already had a linear MRL, so the transformation keeps it the way it was. It's a fixed point. So this is for Weibull. And then gamma, reliability function, G function, expectation, K is simple formula, beta minus 1 over beta plus 1. Of course, it's not the same beta as for the Weibull, but it's still the shape coefficient of the gamma. And we also see that in the limiting cases, when beta is equal to 1, we have the exponential, so k equals 0. And when beta goes to infinity, k goes to 1, and it's the deterministic case. So and we can check from here that when beta goes to 1, we get the exponential distribution. G of t equal, so this, I don't know, there was some kind of maybe a character font problem, because this is simply gt equals t. Right. Now, just a few words, let me take a look at time. My remaining useful life today is 10 minutes, right? But I think we'll be able to make it. If we look at the DJ metric, yeah, there was another one that maybe it was hidden, but no problem. Yeah, if you look at the basically dt prime in the image space, it's dg over dt times dt, of course. So d over dt, it is of the variable time acceleration factor when we go from the initial time referential to the transform time. So we can call this a metric. dg over dt is always non-negative, And when t goes to infinity, it goes to 0. We can see this from the definition of g. As g goes to mu of k, you can see graphically here that, oops, sorry, I went too fast. You can see here that the derivative goes to 0, right? And here it's 0. So and then we can find all those formulas which can be useful to calculate. We have the failure rate and the reliability function and the k coefficient. So an example: Weibull with beta equal 2, the so-called Rayleigh distribution, which basically has a failure rate which is a linear function of time. We take eta equals square root of 2 to make things easier, because the reliability function is then expressed like this. And we have an explicit expression for the mean residual life. And then we can find k. And in that case, k equals pi over 2 minus 1, which is 0.57 approximately. So here we have several functions. You have the mean residual life, v of t. You have its derivative in light blue. Then you have g of t, which has a S shape, and then the metric dg over dt. So we can see that it has in fact, a maximum. So it's an inflection point in g. G has a S shape, so it has an inflection point, which is otherwise stated the maximum of dg over dt. So it means that the acceleration of time, the time speeds up and then it slows down, actually. And in the case of, if we compare Weibull and gamma for approximately the same value of k, Weibull with beta equal 2, so k is 0.57, and gamma with its beta equal to 3, if k equals 0.5. So we have the two curves. The orange one is gamma, and the blue one is Weibull. The two dg over dt curves, they have the same shape, but the peak of the Rayleigh Weibull is higher. And then we can calculate even the maximum. So it's 0.87 in one case, 0.8 in the other. Then an interesting property, and I ask you to believe me, but you can derive it yourself as an exercise. From the study of the second derivative of g of t, we can find the following property. If v of t, the mean remaining residual life, is convex, which is frequently the case, and if g of t has an inflection point, call it t star, then for the time after this inflection point, k gives an upper bound on the average RUL loss rate, dv over dt. So in our case here, we can see that in the examples I took, you can see the inflection point here, 0.8, 0.87. So we can see that after 0.87, the average loss rate of RUL will be less than 0.57 or 0.50, depending whether you look at Rayleigh or gamma. So what does it say? It says that after some time, we have a bound on how quickly the MRL will decrease. It will decrease actually less quickly than in the beginning. Do I still have the connection? Yes. I hope.
Yes, yes.
Yes, okay, good. Yeah. All right. So now, last example. As mentioned in the beginning, sometimes a failure can be replaced with a pseudo failure, and in PHM we are usually interested in that. We have some health indicator. Think, for instance, of the size of the crack or something else that crosses a threshold, and we are interested in how, in when it's going to cross the threshold, because it means that the function is lost. Crack is an easy example, but there are many other examples in various kinds of physical phenomena. So in that case, the remaining useful life is the time from now until when it will cross the threshold. And for instance, if we take the process, model the process as a Wiener process with drift, So it has a variance, let's say sigma square, and a drift parameter nu, which means that the increment is normally distributed with mean nu t and variance sigma square t. And then the time to reach the threshold has an inverse Gaussian distribution, which is well known. Then we can find the G transformation, and the K coefficient is given by this. And we see that K is less than 1, provided we have this inequality. Sigma square is less than nu z. And that means actually that the fluctuations, which are measured by the variance, are small enough as compared to the drift, which is measured by the parameter nu. Another way to say this is we have this equality. Z or Z is the size of the, let's call it the size of the crack that we want to reach. And the right-hand side is, well, the time to reach this is, let's say to reach Z, you need the time Z divided by nu, okay? And in fact, this shows that the average to reach the standard deviation is less than the average. So if what does it mean? If the fluctuations were too high, we would not be sure to actually reach this point. And so this is how the transformation would not work. But when the fluctuation is smaller in terms of then it can work out and can be very useful. I'll give you a very small example, but this is just to illustrate that in the railway business we are interested in that kind of thing, because there are, for instance, track geometries, degradations, and what. But I would need the full screen for this. But so we can see you have fluctuations. So we in the process is actually a fairly good description, and we are interested in when the threshold will be crossed, and then we can use that in order to choose the best maintenance policy, particular tamping, so as to avoid these thresholds to be crossed. Because if the track geometry is too far from the normal, then we have to renovate the track actually. So this can be used in order to optimize the maintenance. Model the track geometry degradation. The occurrence of isolated effects is still something else, but modeling the tamping recovery and then decide on the best maintenance policy. Okay, so to end, we can briefly say a few words about multiple failure and degradation modes. Because so far, everything we have done basically assumes that the time to failure is, the failure basically is caused by one single degradation mode, which can have this or that property, linear in time or not, but it's a single degradation mode. In practice, you often have concurrent degradation modes, each of which may lead to a failure. So we don't know which one will cause the failure first. But let's take a very simple example, where the first degradation mode is a constant failure rate. So it's like an exponential time to failure. V of t is constant, 1 over lambda. And the second so-called degradation mode, it's deterministic aging. The asset simply has a finite lifetime, T1. So after T1, no matter what, the asset expires. So if it was only that mode, this would be the mean residual life. So then we can look at these usual functions for those two concurrent modes. And for that, and why is it interesting? Because in electronics, you have many electronic systems which has a constant failure rate while they are within their life expectancy, but which definitely have a finite life expectancy. And engineers often forget this, which is not good. So if the two parameters are the failure rate lambda and the finite lifetime T1, if the product is very high, then the T1, in other words, is much greater than the MTTF if it was only that mode. So the dominant mode is exponential. So then in that case, we can see that the reliability function looks like exponential. And in the opposite extreme, if the finite life is much smaller than 1 over lambda, the dominant behavior will be precisely that lifetime. And it turns out that it's a uniform distribution, because actually it's equally likely for the failure to happen between now and the end of life. So we can check that by looking at the reliability function, and then by looking at the MRL. This is in the case of where the T1 final life is much smaller than the 1 over lambda, and this is much larger, and this is a case where it is much smaller. So where it converges towards uniform distribution. I would have expected that it would converge to a deterministic distribution, but there's still the element of random failures, which is still there, and this is what makes it uniform. So and in that case, you have the coefficient of variation. A is lambda T1, and you can see the K factor goes down as A increases, because as A increases, the coefficient of variation increases, and the slope goes down to 0. And at the opposite end, when this coefficient goes to 0, the coefficient of variation goes towards the one of a uniform distribution. But this is an example. And so if you look at the MRL and the famous dg over dt metric, so in this case, the constant failure rate dominates. So we have a constant dg over dt until the end. In the end, it jumps because we reach the end of life. And the MRL converges. It is as a slope, it goes to 1/2, which is like a uniform distribution. And on the right, where actually the finite time is much smaller than 1 over lambda. Basically, this is approximately constant because you can see the scale. It doesn't change very much. And the mean remaining life is that of a uniform distribution. It's a linear slope. So the two opposite ends. So conclusions and future research. So what I hope to have shown is that if on physical grounds we can reasonably assume that the mean residual life decreases linearly with time, as is the case in some railway examples and elsewhere, then we can estimate the coefficient K, which is the average RUL loss rate, from the failure data or from the pseudo-failure data, or it could be obtained from estimating the coefficient of variation of the TTF or the RUL. And then we can obtain a confidence interval for the RUL. And it can be generalized to the MRL, which is not linear, but piecewise linear function of time. Then if we deal with two parameter distributions, such as Weibull, gamma, inverse, Gaussian, you can add log normal, etc. to the list, various kinds of degradation processes, then we can find a time transformation that converts that distribution into one which has an MRL linear in time, like in the special case. And then the previous methods are applicable and using the non-linear transformation. And we can find the coefficient K as a function of the shape parameters, not the scale, but the shape parameters of the distribution. And furthermore, if the mean remaining life is convex, then you can find a point in time beyond which this parameter K is an upper bound on the average RUL loss rate. So this is what we have now, and we are applying it to various examples. And directions for future research, the key point really is the link between the coefficient of variation and the average RUL loss rate. The lower variability, that is the lower coefficient of variation, means the higher RUL loss rate, K. And less uncertainty, more determinism in the RUL. And the two extremes, k equals 0, coefficient of variation 1, it is the exponential, and the opposite extreme, k equals 1, CV equals 0, it is deterministic. There's been some recent research by Atamuradov and others, which have shown that it's possible to use changes in the coefficient of variation of extracted features, features in the sense of PHM, to perform fault detection. So question one may raise is perhaps that health indicators coefficient of variation can be used as proxy for the RUL coefficient of variations when we don't have the RUL. So this is an idea. The metric dg to dt, it's a measure of time accelerations, and of course it has implications for maintenance. For instance, one could think of maintaining just before time accelerates, because this is when things are going to become quote-unquote dangerous. Then there's a whole theme, the whole question of dynamic estimation of the metric from data, possibly by machine learning, or maybe Bayesian in any case. So estimate the transformation GT or its derivative dg over dt from field data, and then from that you can derive the mean remain life, residual life of t. Then of course it would be useful to study concurrent failure modes. We just showed a very simple example, and we saw it's already complex, and redundant structures, various kinds of redundancies. And last but not least, of course, use all of that to optimize maintenance, in particular through predictive maintenance, but not only. So a list of references. There's this book by Baniewicz in Toronto, which I believe is not maybe known enough, Remaining Useful Life in Theory and Practice. It's about more than 10 years old. It's still interesting. Of course, Barlow and Proshan is the ancestor. Recent work by Berenguer and his team, Atamuradov mentioned, survey of remaining useful life estimation methods. Krivtsov actually has the work on the Gini index, which is a way to measure the asymmetry in distributions, and there's some relevance to this. And then two conferences, two lectures I gave recently. And I'm currently working on the paper of which you had some kind of a preview, and I wish to acknowledge people with whom I've had very useful discussions. So thank you very much. I hope we did not exceed the time too much, and thank you for your interest. And if we still have a few minutes, of course, I would be pleased to try to answer questions.
Of course. Thanks a lot. Very impressive presentation. I personally liked it, and I hope everyone else as well. So I propose to give a very small clap digitally.
Thank you.
And let's ask if there are any questions in the audience. I may have a question myself, but first let's do a round. Tito.
Yeah, thanks a lot for the presentation. It's interesting to see how you connect the fields of reliability engineering and the remaining useful life concepts. But what I see is that you use a lot of the existing equations, and you construct them in some new concept like the MRL. But is now the main benefit of that the possibility to have these confidence bounds on the RUL? Is that?
Yes, I think so. I think the main contribution is that, as well as trying to use this, of course, for maintenance, but it is something I will not really dwell on here. Yeah, and to do this, of course, it's not in the fully general case, but already the class of distributions which are two-parameter distributions is already covers quite a wide class, I think.
Yeah. Okay. And it's also a way of I think interpreting what it means. So by introducing this MRL, it's also a way of looking at how things degrade and what it means. So I think it's quite a nice way of looking at these equations and
I think what is particularly interesting, in my opinion, is this G function, which I think deserves to be studied a lot more, because it can give us hints as to how things actually. I mean, it can give us insights into what's going on within the distribution, if I can say it so.
Yeah, that's why you suggested to look at this DGDT, and that might be a good trigger for doing maintenance before you get this acceleration point.
Yeah, could be.
Yeah. Okay. Nice. Thanks.
Right. I may have a question,
please,
myself, if I may. Just I was wondering, is in the end this something that we could apply to, various different sorts of applications or also different industries? I can imagine that, of course, for you the main focus would have been on railway maintenance, right?
Yeah.
But could you maybe elaborate a bit on that? So
the question is to which fields it could be applied to, or is your specific question about railways?
No, indeed. Of whether it can also almost exactly the same be applied to other
industries, it is very, very general. In railways, we are interested in track degradations, in wheel wear and things like that. But you could also think of, for instance, if you think about filters. These are things that build up dust, and there's a process of dust material agglomeration which can be modeled, and this is kind of degradation. If you think of cracks in nuclear power plants, for instance, a very frightening topic, but there are people in nuclear power plants who are trying to prolong the life of the plants that were built 40 years ago, because they don't want to build new ones. So they are very interested in how fast those cracks can grow, and this is precisely the type of degradations we could consider. So I could think of many other cases. So it's quite, I think it's quite general, definitely not limited to railways.
No, I can see. Very nice. Thank you.
Somebody?
I see a hand of Stefan Weijers.
Yes, thank you for the presentation. I think it's a very elegant way to describe this remaining lifetime. Just a question, could an application also be on the reduction of pipe thickness in pressure pipes?
Yeah. Absolutely.
It's also something which degrades linear. The question, of course, is can we have a nice way of estimation to estimate it over time without using this destructive method? But I have the feel that it could be applicable also in that area. Can you comment on that?
Yeah, I think so, because this is clearly, whether it's linear, I'm not sure. I'm really not an expert in that field, but this is clearly a phenomenon of degradation that, if unchecked, will have very undesirable consequences. So, then how you measure, what are the indicators that you can use in order to estimate the degradation? I don't know, that's the point you raised, but to be looked at. But I think once we have such indicators, the whole machinery can be applied. Could be applied.
Yeah, thanks. Oh, thanks.
And by the way, what I would like to say also is that if some of you would like to cooperate on some projects and you would like to provide some data, that is something that we could possibly work on from the Lulia point of view, I think. So just you can discuss it later on. You can send me emails, etc.
Yes, could be interesting to look if we can apply this method for the pipe case, which is also a case within this project. Yeah, thanks a lot.
Yeah, thank you. If my details are here.
All right. Yeah, maybe one small final question, as I see Nubia.
Yes, thank you for your presentation, Professor. It was really incredible. I have a question. If I have a component with multiple failures mode, can I apply also this technique? Because, for example, I have not just one remaining for user for life prediction, but multiples.
Yeah, that's a good question. And in the last part of the talk, I tried to address one special case, and you can see it's already quite complex, because at least the only way I was able to deal with it, but doesn't mean that it's the only way, was to derive the reliability function and the mean residual life. But maybe another way, and this is should be ongoing research, would be to look directly at this G transformation, etc., or at the two phenomena degradation modes together, and see how you could build a picture of the complex structure. So yes, this is ongoing work, but you're right, it's a fundamental question, because in most cases you have concurrent failure modes or concurrent degradation modes.
Yes,
so
yes.
either there's a dominant one, you can choose to forget the other ones, or not. And if not, then you do have to have a complete picture.
Yeah, because just to context, in my case, I have, for example, erosion cavitation in impellers, and these both modes, they really can got really close the importance of each. So to get this, I have the remaining for useful life, but my difficulty is see how this distribution goes.
How they conflict, and who, there's a competition, sometimes called a competition, who wins basically in the two. There have been some work on this in literature, but yeah.
Okay, thank you so much.
If you, I would be interested if you can maybe send us examples.
Okay, yeah, we can talk for sure. Thank you so much.
Thank you.
All right. Okay then. Thanks a lot. Thanks again, Professor, for your very nice presentation. Thanks everyone for attending. And looking at the calendar, I see the next colloquium will be on the 7th of April, given by Professor John Andrews. So hope to see everybody of you there again. Bye-bye, everyone.
Thank you. Thank you very much for inviting me. Thank you for comments.
Thanks once more.
Thank you.
Bye-bye.
Thank you.